Well, then I'm going to get started with material. And we'll jump right into 6-7. Now, actually, let me talk about what we're getting at. All right. So 6-7 is going to be all about limits. All right. And the big question that 6-7 and 6-8 are going to be trying to answer is, how do we integrate when one of the bounds on our integration is either an asymptote or infinity. All right. So how do we deal with integration when one of our bounds is an asymptote or infinity? And the short version of that is we use limits. Okay. So we'll utilize limits to do that. And so 6-7 deals with, well, how do we calculate certain limits? Limits, especially that are by asymptotes or go out to infinity. All right. So 6-7 is use of limits, and then 6-8 is let's put those things in integration and use them in integration. Now 6-7 goes sort of hard in the paint on limits. All right. So it goes really deep into limits. And especially it goes into L'Hopital's rule. And 6-8, most of the time we don't need that deep of an understanding. Okay. But 6-7 is, let's say, overly thorough. Does that work? So that's the idea. That's what we're trying to do. So that's why the title of 6-7 is L'Hopital's rule. L'Hopital is a French mathematician, so that's the origins. So let's take a look at some basic limits to start out with. Let's take the limit of 5 over x squared as x gets closer and closer to 0. Now, if x gets closer and closer to 0, then in that fraction, 5 over x squared, the denominator is getting closer and closer to 0 all the time. That makes sense. If the denominator is getting closer and closer to 0 and the numerator is staying the same, that means the total fraction is getting larger and larger and larger. So as the denominator gets bigger, the fraction gets smaller, and vice versa. If the denominator gets really, really small, the fraction gets really, really large. Okay, like 0.01, 0.001. So as x goes to 0, in that first one, the limit of 5 over x squared is infinity. And the reverse is also true. If we have a fraction where the top is staying the same and the bottom is getting really, really, really big, like 3/8x, take the limit of 3/8x as x goes to infinity. That means the denominator is getting really, really huge. The numerator stays at 3, so like 3/1,000,000, 3/1,billion. That means the fraction's getting really, really, really small. So the limit of 3/8x is going to be 0. All right. I would say that sort of reasoning is probably the most common reasoning that we're going to see when we get into 6a. All right. It's just saying that, well, if we have a denominator with a variable in it, as x gets closer to 0, our denominator gets closer to 0, then the whole fraction gets really, really big. If the denominator gets really, really big, that means the whole fraction gets closer and closer to 0. So that's one of the main takeaways of limits. And hopefully you saw that in Calc 1 when you went through Calc 1. Now, also, hopefully you've seen in Calc 1. If I take the limit as x goes to 0 of something like x/x, or something like 5x/3x, and it doesn't matter. Well, it does matter, but I'll say it this way. I want you to notice that if you just plugged in 0, you'd end up with 0/0, which is an undefined fraction, because we're dividing by 0, but also our numerator is 0, right? So in our previous slide, the denominator was getting closer and closer to 0, but the numerator wasn't changing. This time, they're both getting closer to 0. So this is undefined if you just plug it in. However, we have one technique that we could have done, if you remember. And that technique is just algebraically simplify. This one's pretty easy to algebraically simplify. It's x/x, the x's will cancel out, you'll get 1/1. Limit of 1/1 is 1, no matter what you plug in. So, again, I'm just trying to review some techniques that you should have probably seen in Calc 1. One technique is algebraically simplify. Another technique that we just saw was the relationship between our denominator going to 0 or our denominator going to infinity while the numerator stays the same. Does that make sense? Now, not every undefined fraction is going to end up with limit of 1. If I take limit as x goes to 0, 5x/3x, algebraically simplifying 5x/3x gives me 5/3. And so this time, the limit is 5/3. Notice, by the way, when you plugged in the 0, you got the exact same thing, but the limit looks different depending on how the algebraic simplification went. And that's true with infinity as well. Limit as x goes to infinity of x over x. We could algebraically simplify. Now, by the way, let me restate this. If you just plugged in infinity, and by plugging in infinity, I mean that really loosely. Don't mean we're actually plugging in a number called infinity, I'm just saying. If I plug in infinity, the top is going to go off to infinity, the bottom is going to go off to infinity. And so infinity over infinity, again, is an undefined thing. That fraction has limit of 1. But if we did, let's say 1x over 4x, that also, as x goes to infinity, that also can be algebraically simplified into 1/4. So the limit of that is 1/4. In other words, if we get the form 0 over 0, or if we get the form infinity over infinity, then our limit may be anything. Could be any real number, could also be infinity, could also be 0, could also be, a negative number. I don't have any of those up there, but that's the idea. Okay. So these forms, 0 over 0 and infinity over infinity, are in some cases, well, not in some cases, they are special cases. All right. So that's the other one I just wrote on the board. That makes sense. Those forms are what's known as indeterminate forms. They're called indeterminate because if I know my fraction when I plug in 0, or if I plug in infinity, or if I plug in any other number, yields 0 over 0 or infinity over infinity, I really can't tell what the outcome of the limit is going to be. So they're indeterminate, they're undetermined. Okay. So if we have one of these forms, we want to have tools to figure out what the limit is going to be. Obviously, these first two limits that we looked at, those are not indeterminate forms. Those are just standard. That's if I plugged in the top, I got 5 over 0. If I plugged in the bottom, I get 3 over infinity. Those are not indeterminate. Because I know if the numerator stays the same, denominator gets really, really big, then the whole fraction is going to 0. I know if the numerator stays the same, denominator goes to 0, the whole fraction is getting really, really big. Okay. So these first two are not indeterminate forms, but things like x over x, 5x over 3x, 1x over 4x, those do give me indeterminate forms. Okay. Now, those are the two that we're going to deal with most often, the 0 over 0 and the infinity over infinity. But there are other indeterminate forms. 0 times infinity is indeterminate. 1 to the infinite power is indeterminate. If you plug in something and you get 1 to an infinite power, that's indeterminate. 0 to the 0 power, also indeterminate. Infinity minus infinity, also indeterminate. And when we run across these, we'll see a technique later, we'll see a couple of techniques later that, where we can actually figure out what the limit's going to be. All right? So these are indeterminate forms in the context of limits. You just plug in a number and you get 0 times infinity, you go, that's an indeterminate form. Let's see what it actually is. Now, we're gonna take a few examples here and talk through some of the understanding about limits, especially in this case as x goes to infinity. So let's take the limit of 5x to the 4th divided by 7x squared minus 3. And we're taking that limit as x goes to infinity. And then on the second one, we have limit 3x plus 7 divided by the quantity x to the 3rd plus 5x minus 8 as x goes to infinity. I'm going to go over here. Now think about plugging in infinity. As x gets really, really big, the numerator is going to get really, really big, right? So when I say plug in, I mean in terms of limits. So as x goes to infinity, the numerator is going to go to infinity. It's going to get really, really big. As x goes to infinity, also the denominator is going to go to infinity. So this is that indeterminate form, infinity over infinity. Anybody know what the limit of this thing's going to be?
Infinity,
Infinity. How'd you know that?
because the top exponent is larger than the denominator exponent.
Exactly. The top is growing faster than the bottom. The numerator is growing faster than the bottom. The denominator, excuse me. And the reverse is true here. The numerator has higher exponent. So even though we have this indeterminate form, higher exponent controls the entire fraction. And if you don't think, if you want to get insight of why that happens, just like plug in 10, you're going to get 3 times 10 plus 7 over 10 to the 3rd is like 1,000. And then when you plug in, I'm just taking x to the 1st. You can multiply that by 3 if you wanted to add 7. But if you had 100 in for your x to the 1st, x to the 3rd is going to be 100 to the 3rd power. Something like, I think that's 1,000,000, is that right? 100 to the 3rd power is 1,000,000. Notice that this is a smaller fraction than this one's. So in these, the faster growth. Now, when I say faster growth, I mean faster order of growth. I'm ignoring the coefficients, and I'm just saying which one has the higher exponents. The higher exponents are going to determine that. So this one is going to be infinity because we have the faster growth on top. And this one is going to be 0 because we have the faster growth on the bottom. Now, by the way, just so we're all on the same page, if you have limit as x goes to 3 of 5x to the 4th divided by 7x squared minus 3, that is not going to be infinity, right? If I want to find this limit as x goes to 3, I'm just going to plug in 3. That is not an indeterminate form. So whenever I have something that's not an indeterminate form, I'm just plugging in the number. If I can. 5 times 3 to the third, or excuse me, 3 to the 4th is 405. Well, that's squared, thingy. 7 times 3 squared minus 3 is 60. You can simplify that if you wanted to, but my point is, we're going to do a lot of versions with indeterminate forms. Don't forget, this technique is only for indeterminate forms. If we have something that doesn't have an indeterminate form, we're just going to plug that value in and figure out what the limit is by plugging it. Okay. Again, that's just a Calc 1 technique. Now, here's where L'Hopital's rule comes into play. L'Hopital's rule says, if we have an indeterminate form of 0 over 0 or infinity over infinity, then what we can do is say that the limit of the fraction is the same thing as another limit. And that other limit is going to take our fraction and it's going to take the derivative of the numerator divided by the derivative of the denominator. So instead of comparing the actual f and g, numerator, denominator, you can compare the derivatives of that. The derivative of the numerator and the derivative of the denominator. Now, we can actually apply this here if we wanted to. Or here if we wanted to. Let's just do this second one, okay? Now, we saw that it's a faster order growth on the bottom, so the whole thing's going to 0. If you wanted to prove this using L'Hopital's rule, you first start by saying, do I have an indeterminate form? And yes, I do have an indeterminate form. That's infinity over infinity. So I know that this limit as x goes to infinity is going to be the same as the limit of x goes to infinity of what happens when I take the derivative of the top. Well, the derivative of the top becomes 3. And the derivative of the bottom becomes 3x squared plus 5. That's my L'Hopital's. I usually just write LH. Something like that. That's L'Hopital's rule. And if I didn't know that this is a faster order of growth, now I can see what's happening here. My numerator is staying the same here. My denominator is getting really, really big. So this brings this type of problem back to the limit problems we dealt with in the very first slide. Denominator is growing really, really fast. Numerator is staying put. So you end up with a 0. Does that make sense? Now, be careful. You cannot use L'Hopital's rule on something like this, because this is not in that indeterminate form. So you cannot use L'Hopital's rule on anything other than infinity over infinity and 0 over 0. Those two indeterminate forms are the only times you can use L'Hopital's rule. And by the way, if you think about why this goes to infinity and why the faster growth will always of polynomials, if I have polynomial over polynomial, why the faster growth is always going to end up determining whether it goes off to infinity or to 0. Think about taking derivatives of polynomials. On this one, if you take L'Hopital's rule, you get 20x to the third divided by 14x. So this was infinity over infinity, so I could use L'Hopital's rule. By the way, that's also infinity over infinity. So if you wanted to, you could do another L'Hopital's rule. You could also cancel. You get 60x squared over 14. And basically what we're saying is if we have polynomial divided by polynomial, you start taking those derivatives. The one that's going to go to a constant after a certain number of derivatives is the polynomial of smaller degree. Does that make sense? Polynomials of smaller degree are going to get to the constant before the polynomial of the larger. And since larger in this case is on top, that means the numerator is growing, denominator is staying the same, so it's going to infinity. So if we have polynomial over polynomial, L'Hopital's rule kind of gives us why the larger growth, the higher degree polynomial, is going to determine where the entire rational expression goes to in terms of limits. Is that okay? All right. So that's kind of nice thing about L'Hopital's rule. We can deal with polynomials over polynomials now really quickly. We also can deal with things like this, which are not polynomials over polynomials, and maybe not obvious what the limit is going to be. So some uglier type limits. Here we have e to the 2x minus 1 over x. E to the 2x minus 1, that's all in the numerator, over x. And we're going to take the limit of that fraction as x goes to 0. Now, if you just plugged in 0, in the top, e to the 0 is 1. So you get 1 minus 1, which is 0 on the top. And then you get 0 in the denominator too. 0 in the numerator, 0 in the denominator. So we do have the indeterminate form of 0 over 0. Now we use L'Hopital's rule. Be careful when you do L'Hopital's rule, it's still limit as x goes to the same number. All right, L'Hopital's rule has to be limit as x goes to the same number. So don't change those numbers. And then I'm going to take a derivative of the top. Well, the derivative of e to the 2x is 2e to the 2x. The derivative of -1 is 0. And the derivative of x is 1. Now I can plug in 0 and see what I get. And if we plug in 0, it turns out you get the number 2. So that limit is actually 2 using L'Hopital's rule. That might be a hard thing to see if you graphed it. Might not be, I don't know. I don't graph that one. But 2 is the limit. Using L'Hopital's rule. Makes this problem much easier to do, right? Derivative of the top, derivative of the bottom. And then we're moving on. Now we've done polynomials over polynomials going off to infinity, where one of the polynomials had larger degree than the other. What about if the polynomials have the same degree? So limit as x goes to infinity of the rational expression 4x squared plus 3x minus 9 divided by 3x squared minus 4x plus 12. By the way, anybody know what this is off the top of their head?
4/3.
4/3, yeah. So it's going at the same rate. And so what's happening, so they're same degree. The x squared terms in the top and the x squared term in the bottom are going to be the most influential as you get really, really big numbers. So those most influential are going to basically dominate both the numerator and the denominator. So it's going to act like 4x squared over 3x squared, which simplifies to 4/3. Now, you can also do this with L'Hopital's rule as well. That's what I'll do right now to show us that sort of our intuition is right. So if we want to do this with L'Hopital's rule, first off, acknowledge that we have infinity over infinity. Derivative of the top would be 8x plus 3. Derivative of the bottom would be 6x minus 4. That's still infinity over infinity. So I can take another L'Hopital's rule. Notice I can just do L'Hopital's rule as many times as I get infinity over infinity till I don't get that. So we're going to take limit as x goes to infinity. Derivative of the top is 8. Derivative of the bottom is 6. By the way, that 8 came from the 4 times the 2. 6 came from 3 times the 2. So the derivative kept multiplying by exponents. But 8/6, I'm trying to get at, 8/6 has got to be the same thing as 4/3. Okay. And now you see if you have polynomial over polynomial and they're of the same degree, then you can kind of ignore all this other stuff and just look at the highest degree term on top versus the highest degree term on bottom. And if they're the same degree, all we do is cancel out everything and get 4/3. Again, that's only when x goes to infinity. If x were going to 15, we just plug in 15, right? We don't have the indeterminate form. So that's only as x goes to infinity. There. So we're just gonna do a look in state review. Where is this limit going?
Infinity.
Close. It's very, this one's a little bit tricky. It is going to infinity. If we looked at absolute values, technically this one goes to negative infinity.
Oh,
All right, because of that negative coefficient on the bottom. So that is one little thing to watch out for. Your coefficients being positive or negative, both positive. Everything I've done so far, my lead term has always had positive coefficient over positive coefficient. But this one having negative coefficient on the lead term on the bottom, if you apply L'Hopital's rule, you'll see that it'll be a really big number divided by the -4. Okay, so this one's actually going to negative infinity. But yeah, the right idea, it's just. And that's why I put this here, right? Be careful of that little thing, those positive, negative tricks. What's the limit as x goes to infinity of the natural log of x divided by x? Just so you know, as x gets bigger, natural log of x also gets bigger, just at a pretty slow rate. So this still is the indeterminate form, infinity over infinity. You can either compare growth rates, or if you don't know the comparative growth rates, you can use L'Hopital's rule. That's what I'll show. So that we can compare growth rates in the future sections. So if you use L'Hopital's rule, let me do the derivative of the bottom first. That's 1. Derivative of the top is 1 over x. By the way, 1 over x over 1 is just 1 over x, right? So as x gets really big, this goes back to that first slide. X gets really big, it's in the denominator. The whole limit is getting closer to 0. Is that okay? And this also shows you, oh, I didn't write the other one down. I'll erase it. This also shows you if the limit is 0, that means the denominator is getting bigger a lot faster than the numerator as x gets really big. Okay. So that means natural log has a slower growth than x. Which should make sense. If you graphed out natural log, you'd see it's a very slow growth. And if you graphed x, you can see as it gets bigger fast. You guys know what I mean by that? Good. I'll leave it at that. Now, other things we can do. So L'Hopital's rule uses the indeterminate form 0 over 0 or infinity over infinity. Those are the only two forms we can use L'Hopital's rule with, right? To have that fraction form. If I don't have the fraction form, if I have something like e to the x times 1 over x. And let's take the limit as x goes to infinity. If you think about plugging in infinity, e to the infinity is infinity, right? Going really, really big. 1 over infinity is like a 0. So this is the indeterminate form, infinite times 0. Remember, another indeterminate form is infinity times 0. This indeterminate form usually is pretty easy to manipulate and rewrite into a L'Hopital's rule type indeterminate form, 0 over 0 or infinity over infinity. So let me do that. If you get infinite times 0, we just rewrite that. This one's fairly straightforward to rewrite. In this case, I'm going to do e to the x over x. And if I examine, now I plug in infinity, I get infinity over infinity. So now I can use L'Hopital's rule if I want. By the way, which one of these has faster growth? E to the x or x? E to the x has faster growth, right? As x gets really, really big. I'll do L'Hopital's rule, but if you see, oh yeah, the top has much faster growth, then you can skip right to the end. Or if you see like the bottom has much faster growth, you can skip to the end. Here, we'll go through the steps though, the algebraic steps. So derivative of e to the x is just e to the x. Derivative of x is 1. The top is growing, the bottom is staying the same, so the whole fraction goes off to infinity. Is that right? Again, once you kind of figure out, oh yeah, e to the x is a faster growth than x. If you want to say, oh, then the top grows faster than the bottom, as x goes to infinity, the whole thing's got to go into infinity. Or if over here you knew that the bottom grew faster than the top, you could say bottom grows faster than the top, therefore the whole thing's going to go to 0. Okay, L'Hopital's rule lets you see those things. And if you don't know the comparative growth rates, L'Hopital's rule kind of tells you what those are. Tells you that e to the x grows faster than any polynomial, because notice as you keep taking derivatives of e to the x, you're just going to get back e to the x. As you take derivatives of polynomials, they'll eventually get to a constant on the bottom. So e to the x has faster growth than does any polynomial. Okay. So those are the major techniques. The L'Hopital's rule, major techniques, are what I just wrote, polynomial over polynomial, or, you know, something like this, or something like this, something like this, right? We end up with infinity over infinity, or we rewrite it to make it infinity over infinity. We end up with 0 over 0, or we rewrite to make it 0 over 0. And then we just apply L'Hopital's rule or common sense about which one grows faster. The last technique I want to show you is going to be the weird one. All right. It's going to be a really crazy technique. And I'm going to use this classic example in order to demonstrate this technique. Now, I don't expect people to know what this limit is yet, but it might be one you've seen before. So here's the deal. As x goes to infinity, this thing in here, the thing inside the parentheses, becomes 1 plus 0. Oh, did I say, I'm sorry. That should have been x. My apologies. Dang. I miswrote that. So as what happens with the exponent is it becomes infinity. So we get this indeterminate form. Now this indeterminate form is not one that L'Hopital's rule can deal with in this stage. So what we do is we say, let's let y be that limit. You could use any letter, any variable. Obviously, I don't want to use x because I already have the variable x, but any other variable, it doesn't matter. Y is the next variable I thought of. And here's what you do. You have this weird infinity in your exponent. The way you get rid of an exponent is you apply a natural log. So we're going to apply a natural log to both sides. Now, one of the nice things about natural logs is that natural log of the limit is the same thing as the limit of the natural log. So if I apply natural log on the outside, I can take that natural log into the inside. In that way. And then what I do is I start dealing with this limit. And I'm going to rewrite that limit. The reason I use natural log is because one of the rules of natural logs is we can take the exponent and multiply it times natural log and get rid of the exponent. That was the whole trick. Okay. Now, if you think about this, what's the natural log of 1? Well, the natural log of 1 is 0. So as x goes to infinity, this becomes 1. So I have the 0 times infinity version of the indeterminate form now. Now I can rewrite this. The easier way to rewrite the one I want to use. Well, I don't want to try to do natural log to the negative power. That'd be kind of ugly. So I'm going to keep the natural log in the numerator. And that means I take this x and I'm going to turn it into 1 over x in the denominator. Which, if you plug in infinity, is the indeterminate form 0 over 0. Natural log of 1 is 0. And then 1 over infinity is 0. So now let's do L'Hopital's rule. I still get limit as x goes to infinity. Derivative of natural log is 1 over whatever's in the argument. And then I have to multiply times the derivative of that argument. Now, just so you know, 1 over x is the same thing as x to the negative 1. So if you take a derivative, you get negative 1 over x squared. Is that okay? So if u is 1 over x, u prime is negative 1 over x squared. So I'm going to write that as negative 1 over x squared. So that all is the derivative of this top piece. Derivative of the bottom piece is derivative of 1 over x. Derivative of 1 over x is negative 1 over x squared. What's going to happen? Well, negative 1 over x squareds are going to cancel out. What's that?
Is it gonna be 1?
Yep.
Okay.
So we're going to get limit as x goes to infinity of these two things cancel out. So we're just going to be left with 1 over 1 plus 1 over x. And as x goes to infinity, this little fraction here goes to 0. So you just get 1 over 1, which is 1. Now, let me be very, very careful of what we just found here. We have not found the answer to our original problem yet. What we just did is we found the natural log of what we were looking for. All right. So what we found that the natural log of y is equal to 1, which means y is e to the first power. E to the first power is just e. So that means the limit as x goes to infinity of the 1 plus 1 over x to the x power is actually e, or just e to the first power. That make sense? So that's the trick. The trick is if we have these weird indeterminate forms where we have 0 in the exponent or infinity in the exponent, then we can apply natural logs. We can find the limit of the natural log of y using some rewrites. And once you find the limit of the natural log of y, then you can find y by taking e to that whatever power we just found. Is that all right? By the way, I originally said, you may have seen this limit before. This is actually how e is defined. And if you remember like compound interest formula, your compound interest formula, m times per year. Is this. And then it says, well, if you're continuously compounding would be m goes to infinity. Notice it's like 1 plus something over x to the xt. So as m goes to infinity, this piece changes to e to the rt. Okay, and you can use limits to show that if you want. So this is why that happens, compounding interest. M times a year turns into this formula when you compound interest continually. Or continual growth versus growth monthly. Or yearly or quarterly or whatever. Yeah,
If natural log of y equals like 3 or something, would it just be e to the third power?
Yes.
then?
Yep, exactly. So if natural log, if we had the end result being natural log of y equals 3, then y would be e to the third. Exactly.
How could we get natural log of y equal to 3? If like, we're taking the derivative of natural log of 1 plus 1 over x,
Yeah,
how can we get the numerator to be a different number?
well, it definitely have to be a different problem.
Okay.
Yeah, so not in this problem, you couldn't get it to be.
Well, yeah, I mean, like, what causes the number to change? I understand that it can happen, but I just am wondering how that number can change. Would it be like in front of the natural log sign?
So actually, how it happens, I think you have to change this number here.
Okay.
All right, so I think it has to be, the 1 plus 1 over x, I believe you take 1 plus 3 over x. I think that changes it to 3. I have to go through the results, but I'm pretty sure that's it. Think that's what it does. Because then when you take a derivative of the inside function, it's not negative 1 over x to the third, it's like negative 3 over x to the, see, I misspoke. Not negative 1 over x squared, but negative 3 over x squared. But the bottom is still negative 1 over x squared. And then it goes that way. Let me do one more of those, and this time we'll do limit as x goes to 0. I skipped example 7, you can do that on your own if you'd like. But I'm gonna go right to example 8. It's very similar. Except now we have 1 plus x raised to the power of 6 over x. And we're taking the limit as x goes to 0. Again, there's lots of similarities there. Okay. So once again. We have 1 to the infinity as my indeterminate form. When I plug in 0 inside the parentheses, I get 1, and then 6/0 becomes infinity. I guess it depends on which way you approach 0, but could become negative infinity as well. But we'll just say plus and minus. I can't use this indeterminate form with L'Hopital's rule. So I apply natural log to the limit. Again, if I apply natural log, the nice thing about natural log is that the natural log of the limit is the same thing as the limit of the natural log. That is a rule that's non-trivial that I've kind of just said it exists, but that's an important piece to this, that you can bring the natural log inside the limit. So you can bring the natural log inside the limit. And then we can keep rewriting this. By the way, this is kind of a nice rewrite. Here, we have infinity times 0. The easiest way to rewrite that one is to keep the 6 in the numerator, natural log of 1 plus x in the numerator, and then just put the x in the denominator. Now I have 0/0 as my indeterminate form. So now I can use L'Hopital's rule. Derivative of the denominator is really easy, just 1. Derivative of the numerator is going to be, well, we have the 6 times 1 over the argument times the derivative of what's inside the argument. Derivative of what's inside the argument is just a 1, right? Derivative of x is 1. We okay with that? That's just a rewrite. And that's a way to get 6. Now, as x goes to 0, plug in 0 into x, you just get 6/1. 6. Again, we haven't found what we were looking for to begin with. What we found is that the natural log of what we're looking for is 6. So this is the e to the 6th case. So my limit as x goes to 0, 1 plus x to the 6/x is equal to e to the 6th power. By the way, that's not the only way to get e to a different power. You could have done something inside of here and got the e to a different power as well. Any questions about this technique? This applying natural log and then bringing the exponent down and rewriting it? This one's a little bit more straightforward because when you put the x in the denominator, it's a lot easier to take derivatives of x than it is to take derivative of 1 over x. Now, like I said, this is sort of the extreme cases of use of L'Hopital's rule. Most of the things we're gonna see in 6.8, when we integrate close to asymptote, or we integrate out to infinity, are gonna be more of the stuff that we looked at the very, very beginning, like 5 over 3x as x goes to infinity. You know what I'm saying? So stuff like that. This is the really hard limit stuff, the harder calculations. So like I said, they go really into deep waters in 6.7. But in 6.8, when we actually get to the uses that we want to see, the limits that we're going to use are going to be more of those beginning type limits. They're not going to be these real hard ones, typically. So 6.8 is on improper integrals. So improper integrals just means I have a definite integral. Remember that a definite integral just means it's an integration with bounds. Most of the time on definite integrals, if I have a nice continuous function and I have a definite integral, I can just say, well, so if I can integrate f, let me rephrase this. What can I do? So if I can integrate f, if I know the antiderivative, of this continuous function f of x, then I can do that, right? But what if I can't plug in b or I can't plug in a? This is just a fundamental theorem of calculus, right? Fundamental theorem of calculus says this. If I can't simply plug in b or a, then I may be able to use limits. In short, instead of f of b, use limit as x goes to b of that function. Instead of using f of a, use limit as f goes to a of that function. We okay with that? And this is always going to be required if a or b is infinity. If a or b is infinity, then that's always gonna be required. All right? So we get what's called an improper integral when A or B is positive or negative infinity. Or both of them are infinity. One's negative, one's positive infinity. Also, we get an improper integral when we have asymptotes too. Because oftentimes we can't just plug in a number when we have an asymptote there. Does that make sense? So the basics of it is we're gonna use fundamental theorem of calculus, and then we're gonna say instead of just plugging in b, we need to take the limit as x goes to b. And oftentimes I will state we're gonna plug in b when I actually just mean take the limit as x goes to b. From here on out. Now, this integration could yield a real number. So we're gonna take a definite integral, and a lot of times we'll get a real number. If we get a real number, when I integrate that definite integral, I say the integral converges. Okay. So I do this whole thing, this process, I get a real number, I say the integral converges. I do this whole process and I get something that's nonsense or something more likely that comes out as infinity, positive or negative infinity, then I say that my integration diverges. So converges means I get a real number out of the process, diverges means I get infinity out of the process, or something that does not exist out of the process. Okay. This all makes sense? All right, so let's do an example. Let's take and integrate 1 over x squared from 1 to infinity. Okay, I'm gonna rewrite this so I can take an antiderivative a little bit easier. This is x to the minus 2, integrated from 1 to infinity. So when I take an antiderivative, I have to add 1 to the exponent and then divide by my new exponent. Now, just because I'm gonna be dealing with some plugging in infinity, I often like to see these things as fractions with positive exponents. A lot of times they just makes more sense that way. So there we go. Now, normally, using the fundamental rule of calculus, I would just plug in the infinity, the top number, plug in the 1 and subtract it. Well, you can't technically plug in infinity, right? So instead of plugging in infinity, we take the limit as x goes to infinity of -1 over x minus, now we can plug in the number 1. That's okay to plug in. We just saw what this did. This was at the very beginning type stuff of 6, 7. Numerator stays the same, denominator gets really, really big, so this whole fraction goes to 0. So that integration is actually 1. And so we say, shorthandedly, that this integration converges to 1, or is equal to 1 and converges. Because it gave us out a real number. So the language there is converges to 1, or that integration is 1, and therefore it converges. By the way, once you get comfortable doing this, you'll probably skip writing this step. And in fact, you'll hear me a lot linguistically say plug in infinity. When I say plug in infinity, I really mean just take the limit as x goes to infinity. All right? So once you get comfortable with these limits, you just quote plug in infinity, unquote, and see that as a 0. All right, the next one, we are also going to integrate from 1 to infinity, but we're going to integrate 1 over x to the 1/2 power, x to the 0.5 power. This looks very similar to x squared in the denominator. But obviously we have a different power. So that is rewritten as x to the negative 0.5. I do my same trick. I add 1 to the exponent. This time, when you add 1 to the exponent, you get 1 plus negative 0.5 gives you a positive 0.5. So we get 2 times x to the 0.5 power. By the way, 0.5 power is like the square root of x, right? So 2 times the square root of x. Now, again, you can't plug in infinity, but you can take the limit as x goes to infinity. As x gets really, really big, what does the square root of x do?
It's really, really big.
It still gets really, really big, right? So when you plug in infinity, by taking the limit as x goes to infinity, that thing becomes infinity. Minus, when you plug in 1, you get 2 times the square root of 1. Well, infinity minus 2 is just infinity. So this thing, we would say diverges to infinity. Or just diverges. Sometimes people just say diverges when it goes off to infinity. Now, let me talk about how odd that is, how weird that is. Let me try to explain that graphically, what's happening. We have two functions, call one of them f of x. 1 over x squared and I'll call the other one g of x. 1 over x to the 0.5 power. And we're going from 1 to infinity. Both of these are getting really, really close to the x-axis, right? And remember what integration did. Integration essentially takes the area under the curve. So let me try to rewrite that. Let's do 0 less than 1 over x squared. Less than x squared. From x from 1 to I don't know how I do that. There we go. Finished. Good. And then I'll control copy. Paste. There we go. I'm going to change some of the settings. All right. So what we're saying, yeah, I could, is that this red area, this area, even though it goes on forever to the right, it has a finite area, and that area is 1. Which is kind of a weird concept in and of itself. Because this thing has finite length, it's be infinite length, but a finite area. It's really hard to wrap your head around. However, this other curve, this area, even though it's kind of in principle doing the same thing, it's not getting close enough to the x-axis to make the area finite. So that area is infinite. Whereas the red area, because my curve got close enough to the x-axis quickly enough, that red area, it became 1, and the blue area is infinite. Pretty crazy, right? Kind of weird thing. So you may ask, well, how fast do you have to get close to the x-axis to make that area be something that's infinite versus something that's finite? And it turns out 1 over x is the cutoff value. 1 over x to the first. So let's go ahead and do integration of 1 over x with respect to x from 1 to infinity. Well, the antiderivative of 1 over x is natural log of x. And in 6.7, if you recall, I said if you plug in infinity into natural log, it goes to infinity. So when you plug in infinity into natural log, when you take the limit as x goes to infinity of natural log, you actually get infinity. If you plug in 1, you get a 0. Infinity minus 0 is still infinity. So that means this integration diverges. I think diverges because it goes out to infinity. By the way, we don't always have to start at 1. This would be also true if you started at, because you'd have infinity minus natural log of 38, infinity minus any real number is still infinity. Right? And the previous two, whenever we get infinity minus a constant number, still infinity, right? So when we integrated 1 over x to the 0.5, we would have still got infinity. When you had integrated 1 over x squared and got 1, if you started at a different number, you'd get a different number, but it'd still be a real number. Does that make sense? So if you integrated from like 7 out to infinity, it would still converge, 1 over x squared would still converge, but it wouldn't converge to 1, it would converge to a different area under the curve. And so that's something that oftentimes people will make note of. And just note that when you integrate from 1 to infinity, 1 over x to some power, it's going to converge if that power is above 1. And if the power is 1 or below, it's going to diverge. And that would be the same if you started at 10 instead of 1. And that would be the same if you started at 7 instead of 1. All right. Now, I want to skip ahead a little bit because I want to make mention of something else, and then I'll go back. All right. So I'm going to skip ahead to example 7. And I'm going to say, well, what would happen if we integrated 1 over x squared instead of integrating from 1 to infinity? What if we integrated from the asymptote of 0 up to 1? And we'll do the same thing for 1 over x to the 0.5 as well. That's example 8. So this is another way of getting indefinite integrals, is when we're integrating and one of our bounds is the asymptote. You guys know what I mean by that? So if you look at both of these have an asymptote at 0. Okay. So let's do that. And I'll do both of them. So the antiderivative is gonna work the same. We're gonna get -1 over x to the first power. Integrated from 0 to 1. I did that last, what was it, example 1, so I think we're okay there, right? If you haven't, if you don't remember that, we just did it when we did the other one. Now, plugging in 1 is not a problem. The problem comes when we try to plug in 0. We're gonna take the limit as x goes to 0 of -1 over x. As x goes to 0, and technically, by the way, since we're between 1 and 0, x is going to 0 from the positive numbers. Does that make sense? So x is going to 0 just from, so think you're plugging in positive x's, but they're really, really small. So from above. As x goes to 0, that means the denominator gets really, really small. The entire fraction, since we have a -1 on top, is going to -infinity. Does that make sense? -1 over x. As x gets really, really, really small, but x stays positive. -1 over a positive number gives you -infinity. So integrating from 0 to 1, 1 over x squared, that diverges. Some people, again, would say diverges to infinity. Notice that's the opposite of 1 to infinity, isn't it? When we did 1 to infinity, the 1 over x squared converged. Now let's see what happens when we do 0 to 1. 1 over x to the 0.5. Again, I'm going to shorthand this because we just integrated that, so I won't show all the steps of integration. Because last time we saw that we got 2 times square root of x when I integrated 1 over x to the 0.5. Okay, that's from earlier. Well, now I can actually plug in 1. And I can also plug in 0. And we just see that that integration from 0 to 1 is 2. So this integration with 1 over x to the 0.5 respect to x, when you go from 0 to 1, actually converges to 2. And you can imagine where the cutoff is. Just like we had before, but in the reverse order. Now, there is one little exception. It turns out, if this is just 1 over x from 0 to 1, it still diverges. So 1 over x diverges in both cases. But we'll note that if we're integrating from 0 to 1, 1 over x to a power. I'll write it. It converges if that power is below 1. And that same integration diverges if the power is at or above 1. Interesting, huh? So the 0 to 1 and the 1 to infinity are kind of with these types of integrations are reverses of each other in terms of diverge versus converge. All right. By the way, if we were really clever geometrically, we probably would have seen that. Because if you think about the area, let's do this. From 0 to 1, under x to the 1 over x to the 0.5. And then if you think about the area from 1 to infinity of 1 over x squared, you'll notice that these spaces up here are going to match these spaces down here. You guys know what I mean by that? Other than this little block here, other than this little square block, they're the same. They're inverses of each other. And they're inverse of each other for the obvious reason. If you go y equals 1 over x squared, that means, again, let's use positive values for x and y. Take a positive square root of both sides. That means x is equal to 1 over square root of y. Right, or y to the 0.5 power. So basically, they're flipping the roles of x and y's in that sense. That might be overkill on my part, but it's just an interesting observation. That when you integrate from 0 to 1, something like that, there's a connection between integrating from 1 to infinity of that function's inverse. Okay. On positive numbers. Now, obviously, it's not always going to be integration let me rephrase, of 1 over x to the power. You can do any integration you want around the asymptotes or out to infinity. You can do from negative infinity to -2, for instance. That negative infinity makes this an indefinite integral. You can do even stuff like this, integrate from 0 to infinity 4x over x squared plus 1. Let me do that one. And this will be the last one we do. if I had to do this by hand. This is a U substitution. So we'd be integrating 2 times 2x dx over x squared plus 1 from 0 to infinity. When I do my u substitution, the 2x dx becomes my new du. So I get 2 times du on the top. And on the bottom, I get a u. By the way, this integration is no longer from 0 to infinity, because we're dealing with u's now. We'll go natural log of 2 times natural log of u plus a constant. I'll just let my constant be 0. And now if I'm talking about from 0 to infinity, when I back substitute, I get 2 times the natural log of x squared plus 1 plus any constant that I want. Integrated from 0 to infinity. Good, all right, everybody okay with that? So this is just one technique that we used earlier. And now we're saying, after I do that technique, if I have a definite integral, I just plug in the bounds. So if my definite integral is improper, I'll just plug in the improper bounds. When I plug in infinity, this becomes really, really, really big. Natural log of things getting really, really big is going to be infinity when I plug infinity in. When I plug in 0, I get 2 times natural log of 1. Natural log of 1 is 0. So I just get 2 times 0, which is 0. Let's go right, 0. So this integration diverges to infinity, or just is infinity. So some people would say that integration is infinity or yields infinity, diverges to infinity. Any questions about that? So essentially, all of the techniques that we looked at in all of chapter 6, now you can apply. And then if you get a definite integral with bounds that are hard to plug in, where you can't just plug in the bounds, use limits instead of straight plugins.
You changed the bounds? Like filled it?
Yes, yeah, if you wanted to change the bounds, what you would do is you'd say a 0 for x is actually a 1 for u. So you just plug in. So if you wanted to change the bounds, 0 in for x is a 1 for u, and an infinity in for x is an infinity in for u. So if you wanted to do it that way, and then change them back to 0 to infinity, that'd be okay too. I just think it's,
But couldn't we just have where the bounds are 1 to infinity? Don't we?
oh, you could have plugged it in right here, yeah.
But don't we know it's a number over what you can just substitute the u for an x?
Oh, that's a good
So that'd be
observation.
next to the first. and we
Yeah,
know what
so-
divergent.
So we already know bound from 1 to infinity of 1 over u, that diverges. And so we could have said, oh yeah, I already know that this guy is gonna diverge too with bounds from 1 to infinity. That's a very good observation. Yeah, So yes, you could have absolutely done that. You could have absolutely said, oh, at this stage, I know that's gonna diverge. Cause it's like one over u to be integrated from one to infinity. So yes, absolutely, you could have done that, for sure, and that's a very, very nice observation. Not all of them will turn out to be something we already know, but. Yeah, that's a great observation in this case. Any questions about any of this stuff? Now, like I said, we kind of missed a class period. We had one go short, so usually I have more time for questions and things like that at the end before a test. If you do have questions while you're studying for the test, email those to me. I'll try to get back to you. I will be around tomorrow. Saturday, I'll be gone all day, so I won't be around town Saturday. But, yeah, we'll be around tomorrow. So if you do have any questions, let me know. The homeworks are still gonna be due Friday at 5, but the test is due Sunday at 5, okay? All right, I'll see you next week.